We are now ready for our third learning objective. In this learning objective, we are going to try to understand how a buffer works. We know that a buffer resists change to pH. That's its job. We also know what it has in it. It has a weak acid and its conjugate base, or a weak base and its conjugate acid, so it has something weak with its conjugate, its significant quantities. And the question is, how does that do what it's supposed to do? How does that cause a resistance of the change of pH? Now, this learning objective is very important for you because you've got to understand how it works in order to do what's next, which is calculate the pH of a buffer after you add an acid and add a base. If you don't understand what's going on in that, you won't be able to write good reaction equations. So make sure you pay very close attention to this learning objective. We're going to start with a clear question. If we've got a buffer that consists of acetic acid, that's a weak acid, and we see acetic acid written right here. And it also has its conjugate base, salt, so it has its conjugate base, that's this portion here in it. And we take that buffer, and let's draw a little picture of a flask containing that buffer, okay? So we have this buffer in there, and we're going to add to it some base. Now a base has with it hydroxide ions. So we're putting hydroxide ions in there, the base. Which portion of that buffer will the OH minus react with? Think about that, answer the question, and then we'll move on. Well, hopefully you said the acid. What neutralizes a base? Well, an acid does. So the reason you have an acid in a buffer is so that it can neutralize any added base. So the next question is this. We're going to have that exact same buffer that contains a weak acid and its conjugate base in solution. So we have that same flask with that same buffer in it. And this time, instead of adding a base, we're going to add an acid. So we have an H plus, or it could be considered as H3O plus, is being added into that flask. What is going to neutralize that added acid? Did you say the base portion of the buffer? Well, if you did, you're correct. The CH3COO minus, which is the acetate ion, will react with the added acid to neutralize it. So let's kind of examine this with our pictures here. The flask in the middle is our original buffer, and we see that it consists of a weak acid, HA, and that is represented with all of these in solution. And then we've got our weak base, which is the A minus, and that is represented with all of these in solution. So this solution contains both a weak acid and its conjugate base in significant quantities. So let's head towards the left. Let's add the base to this buffer. As we add the base to the buffer, it's the acid that has to neutralize it. So a base is going to be reacting with an acid in this buffer. As we add, let's say we add 1 OH minus, okay? It is going to be neutralized by one of these acids. When this happens, then we see what's on the left after the addition of this base. Well, the HA that I have circled here in the flask gets converted to an A minus. And it is dropping the amount of HAs down. So we have less HA in this flask than we had over here in the original flask. But it increased the amount of A minus. We see that the A minus, we have 1, 2, 3, 4, 5 represented over here, where we only had 1, 2, 3, 4 represented over here. So the A minus is increasing, the HA is decreasing, but we still contain a buffer solution. We still have some of both of these. pH might change a little bit, but we have removed the strong base that we added in. We have neutralized that, so it only changes a small amount. Okay, so let's erase all of this and let's go in the opposite direction. Let us start with our buffer, and now we're going to add added acid, H plus. Or we could think of it as H3O plus. It really doesn't matter. We're adding that into our buffer. It is going in. Well, which portion of this is going to neutralize the added acid? Well, the base portion will, the A minus will. And H plus will react with an A minus and it will turn into HA. So we see that we had 1, 2, 3, 4 here. As we go to the right, we now have only 3. We have dropped the amount of A minus down because we've used some of it to neutralize the acid. But we increased the amount of HA. On the left we had 1, 2, 3, 4 in our original buffer. And as the reaction takes place and it reacted and took on the H plus, we end up increasing the amount. So we see that the HA is going up, the A minus is going down. It is still a buffer, but we used up all of that added acid and it resists change to pH. It may change some because the ratio of acid to base over here is changing, but it won't change a lot because we're taking that acid out of the mix. So we have a couple things to think about here. Why can't you use a strong acid and its conjugate base? For example, why can't you just have HCl and sodium chloride and say that's a buffer? Well, the reason you can't do that is because the HCl, we know 100% ionizes. And you would not have any acid in your solution to neutralize the base. So you would just have a bunch of Cl minuses floating around in solution. And you wouldn't have any HCl. So that's why you need both in a significant quantity, both the acid and the base in significant quantity in your solution. And when you have a strong acid in solution, you don't have any of the HCl actually floating around in that beaker. Now, you can't just add any old weak acid and any old weak base together and make a buffer out of that. You might think, well, you'd have some of both present, but they would just end up reacting with each other. So if we took a weak acid and ammonia and let them put them in the flask, they end up reacting with each other. They have to be conjugates because conjugates of each other don't react with each other. They sit on opposite sides of the equation from each other. Okay, so we learned how to calculate the pH of a buffer in the previous learning objective. Now we're ready to learn how to calculate the pH after you add a strong acid or a strong base. You don't have to add a strong acid or a strong base to a buffer to see it resist change, but we're only going to ask you to calculate the pH after adding a strong acid or a strong base because it's a simpler calculation for us to work through. We remember that a buffer resists change to pH by neutralizing that strong acid or that strong base in solution. So we have to write that reaction, and that's the hardest part about doing these calculations. As we go through and do problems for this, and students are doing them for the first time, they generally can do all the calculations, but they struggle with the very beginning. How do I write the reaction? So really focus on this portion of the lesson. Once we have written the reaction, then we're going to follow a common procedure. And I'm going to walk you through the procedure. The first thing you do is write the reaction. This is going to be a one-way reaction. By that I mean it will go to completion. The reason for that is because one of those things that we add, either the acid or the base that we add, is going to be strong. That strong will react with the weak of the buffer, whatever we need, and the strong component pushes this reaction to completion. With that, we're going to do something called an Icf table instead of an Ice table. F stands for final. It is a way of doing a limiting reactant problem that you've probably not seen before, but it's really handy when the ratios are 1-to-1 in your balanced equation, which is always the case here in this chapter. When we've completed the table, we're going to look at the F line, and we're going to see that we still have a buffer. If we haven't wiped out the buffering capacity, we still have a buffer, and as a buffer we can still determine the pH as we would any other buffer solution. I generally choose to use the Henderson-Hasselbalch equation because I have it memorized and I see that it saves me a lot of effort and time. So let's work this problem. We're going to calculate the pH first of just the buffer, so we see what our starting point is. We have the Henderson-Hasselbalch equation telling me pH equals pKa. That would be the negative log of 1.8 times 10 to the minus 5 plus the log of the base over the acid. Well, here's the base. It's 1 molar. Here's the acid. It is also 1 molar. If both the acid and base concentration are the same, that's the log of 1. The log of 1 is 0. So pH is just equal to the negative log of that Ka value, or the pKa. pH is equal to, in this case, 4.74. And that's the pH of that buffer. Now for the more challenging part. We're going to add a strong base, sodium hydroxide, to that buffer. So we have to think about that buffer and what would react with that strong base. Now the first thing I want you to do is to write this as a net ionic equation. We need to get rid of the spectator ions because they just complicate things and make it difficult to write a good equation. As a strong base, it 100% breaks apart. We're not going to worry about the sodium ions. Anytime I have a strong base, I'm going to write in my reaction OH minus to represent that strong base. And then I consider my buffer. So look back in your notes and look at what is in that buffer and which component of that buffer would neutralize that strong base. Well, it would be the acetic acid. The job of the acid in that buffer is to neutralize any added base. Since the base is strong, it's going to be a one-way reaction. Now don't try to memorize the products. Realize that we have a base and we have an acid, so we're just going to swap the proton. The acid will donate to the base. When the acid gives its proton to the base, we are left with CH3, COO minus, and water. Okay, so we have our reaction. That, like I said, is the most challenging part, so you might want to pause and really think about why did I write that reaction the way I did. Since it's a one-way reaction, we're going to do an Icf table instead of an ICE table. In an Icf table, it's a limiting reactant type problem, and it's really handy to use moles instead of molarity in the equation. So let's get the moles of OH minus first. The moles of OH minus would be equal to the moles of NaOH because there's one hydroxide in there. To get the moles, we'll take the molarity of 0.10 mole per liter times the volume in liters. It's 1 milliliter or 0.1 liter. It's 1 milliliter or 0.001 liter. And that is going to give me 1.0 times 10 to the minus 4 moles. And I can place that into my table. For the moles of the acetic acid, we look at the buffer solution. We know that it's going to be the molarity. Whoops, it's not 0.1 molar. It is 1 mole per liter times how many liters of that buffer. Now they tell me up here in the problem that I had 100 milliliters. So that's 0.1 liter, and that's going to give me 0.1 moles. And I can place that in my table. Now this is a buffer, so it also has the acetate ion present. That came from the sodium acetate. So the moles of acetate would be the same as the moles of sodium acetate. So we take the molarity times the volume. Again, it's 100 milliliters or 0.1 liter, and that gives me 0.1 moles of the acetate ion. And I can put that in the table. I don't care about the water, so I'll scribble that line out. Now here's how you do an Icf table. You don't use variables, you don't use x's. What you do is say this reaction is going to go until it's finished. And it can only go until it uses up the least of the two reactants. So look at those two reactant quantities there. We have 1 times 10 to the minus 4 and 0.1. And we know this reaction is going to go until we use up all of the lesser one. And that's 1.0 times 10 to the minus 4. Now, as in an ICE table, the change line is the reaction taking place. So we are going to use it up the same quantity of this and produce 1.0 times 10 to the minus 4 of that. That is going to consume all of the added base. That's why a buffer works. It uses up and consumes the added base. But it affects the amount of the others. So if I take 0.1 and I use up a little bit, I'm going to have 0.0999. And really to 3 decimal places, it's still 0.100, but I'm going to carry extra places. And I've got 0.1001 over here. Again, according to the rules of significant figure, those two numbers won't change at all, but we'll just carry extra until we finish the problem. At this point, we see that we still have a buffer. We have some weak acid. That's the weak acid. And we have some weak base. That's the weak base. So it's a buffer. And as a buffer, we can use the Henderson-Hasselbalch equation. pH equals pKa. Well, we got the pKa in the previous problem, so I'll go ahead and write that down. Plus the log of the concentration of base over concentration of acid. Well, these aren't concentration. They're moles. But I'm going to tell you something that I haven't told you yet. In the Henderson-Hasselbalch equation, we could put moles of base over moles of acid instead of concentration of base over concentration of acid. And I'm going to show you why that is here in just a minute. But let's go ahead and think about the numbers. For the base, we have 0.1001, and for the acid, we have 0.0999. And when we put those numbers in, we're going to end up not changing the pH at all. Take the log of that ratio. It is so small that it does not change the value of the pH. Now I said I would mention why you can use moles. Let's say we couldn't use moles. Let's say we had to take this term on the right and put in concentrations instead. Well, how do we go from moles to molarity? We divide by volume. So we take our moles of the base and divide by the total volume. The total volume would be 100 milliliters of the one, 1 milliliter of the other, converted to liters because we need moles per liter, and we'd have 0.101 liters. Let's do that for the acid. It would be moles of acid over volume, and it would be the same volume. Since I'm dividing the numerator and the denominator by exactly the same volume, I can use the ratio of moles instead of the ratio of concentrations. So know that the Henderson-Hasselbalch equation, you can plug those moles in instead of molarity. So since moles comes out of the table up here, I can plug the moles directly into the Henderson-Hasselbalch equation and obtain a value. Now you might think, well, of course it didn't change. Of course it resisted change. We have a very low number of volume, 1 milliliter, being added to a whole 100 milliliters of solution. And the concentration of that base is very, very low compared to the concentration of the buffer, which is 1 molar. And you say, well, surely that would not affect the pH no matter what, whether it's a buffer or not. So the next question is just to counter that argument. If I were to add the same quantity of sodium hydroxide to just water, would it also barely change the pH? Well, let's see. The pH of pure water is 7. We know that. So maybe this would change the pH of the pure water. Well, this is just a dilution. We're adding sodium hydroxide to water. So I'm going to use the dilution equation. M1V1 equals M2V2. The molarity of the base to begin with was 0.1 molar, and I had a milliliter of it. The molarity of the base after it's been diluted, I'm trying to solve for, and the total volume after dilution was 101 milliliters. So the molarity of the sodium hydroxide after this dilution is equal to 9.9 times 10 to the minus 4 molar. It brings that concentration down quite a bit. What is that the concentration of? That's the concentration of sodium hydroxide, or after it's dissolved, and we know it breaks apart, that's the concentration of hydroxide. So pH would be the negative log. Nope, not pH. POH. POH would be the negative log of that number. And the pH is 3. POH. Keep saying pH. POH is 3. The pH would be 14 minus 3, which would be 11. So, yes, a tiny amount of sodium hydroxide added to water would take the pH from 7 to 11. That is not resisting the change of pH. You add that same amount to a buffer, we saw no change whatsoever. For our next problem, we're going to add an acid to the same buffer. So we have to figure out how to write this reaction and follow the same procedure. Whenever I come across a strong acid, rather than writing it as HCl in my reaction, I will write it as H3O+, because it 100% ionizes to produce H3O+. It's the H3O+ that gets neutralized by the base of the buffer. So look back at your buffer and identify the base. Well, we had a clear question about that. This is the base. That's what neutralizes the acid. It's a one-way reaction because the strong acid pushes it to completion, and we end up producing, by a proton swap, the acid, the H here, is being donated to the base, and we're left with water as the other product. We will do an Icf table because it's a one-way reaction. We will plug moles into the table. So let's start by determining the moles of H3O+. That would be same as the moles of HCl that I put in there. They gave me the molarity, and that's missing an M. I just now noticed that. That's the molarity. Moles per liter of HCl times the volume in liters is going to give me 0.0004 moles, or 4.0 times 10 to the minus 4 moles. So it's way more moles than we had of sodium hydroxide. Maybe this will change the pH. We're going to put 4.0 times 10 to the minus 4 here. It's the same buffer we had before, and the moles we determined before were 0.1, and I don't care about the water. Okay, so this is being added to the same buffer we've been working on all along. Okay, so we're going to consume the smaller of the two reactants. That is the 4.0 times 10 to the minus 4. Carry that across in the changed line according to the balanced equation. This represents the reaction actually happening until I use up all of the added acid. That's the reason a buffer works. We are neutralizing, reacting out, consuming all of that added strong acid. But that does change the amount of the buffer components. So this is going to drop down to 0.0996. This is going to be increased to 0.1004. And we're ready now again to use the Henderson-Hasselbalch equation. pH equals pKa. Well, I'm using the same buffer. It's got a pKa of 4.74 plus the log of the number of moles of base. So we come up to our F line, and there's the base. I can use the number of moles of base over the number of moles of acid. And guess what? This still does not change it. It takes it down ever so slightly, but to 2 places after the decimal point, which is all we can really know it, it still is 4.74. If we had maybe added 4 milliliters instead of 2 milliliters, I think we'd finally start getting enough in there that the ratio of base to acid will have changed enough to actually bring that pH a little bit down when we're adding this acid. Eventually that's what's going to happen. The pH will drop down as the acid concentration goes up of the buffer and the base concentration goes down enough. We'll see it drop. So that ends learning objective number 3. You've learned how to calculate the pH of a buffer after you add an acid or a base to that buffer. It is a challenging procedure. not to do the work, but to start off with a good reaction. You've got to remember that if you add an acid into the buffer, it reacts with the base of the buffer. If you add a base to the buffer, it reacts with the acid that's in that buffer. Got to write a good first reaction, and then you can proceed with that ICF table. You'll have extra problems that you can watch me work through that are posted in this lesson as well. And once you've done that, then work on those practice problems.